anyone else wants to punch in, you can. Let me make sure that we are recording. Okay, yeah, we are going. Very good. I'll be posting this video on YouTube later on, so if any of you want to watch again, you can. All right, any ideas other than naming reaction equations, oxidation states, and enthalpy? I'll definitely do all of that. Also, this workshop will go on until 2:50. I'll have to cut it then. Yeah, and I had the feeling enthalpy would be one of them. All right. So with that in mind, let's go ahead and start with naming. Let's go past the electron configuration and into naming here. So let's start with ionic formulas. So predict the compound that would be formed by the following combinations. We'll start with calcium and phosphate, okay? So I'm going to put a little text box over here so we can write some directions. So step number 1 is going to be to, let me move this. Move this over. So we're going to have to write the symbols and the charges for each ion they give you. All right. So we have to think about calcium, have to think about phosphate. So we know calcium is Ca. And to figure out its charge, we go to the periodic table. So we come over here and we locate Ca. That is in the second column, group 2A. And group 2A will always be plus 2. We'll write that down. Okay. We'll put the charge up there. And now, I'm going to throw this question to the chat. This will be for you folks. What is the symbol and what is the charge for phosphate? Does anyone remember that one? Phosphate. Now, K is potassium. We're looking for phosphate. So you got PSO4. You're close. You're close. It's PO4. PO4 is correct. You're even closer. So PO4 2 negative is close to that. Check your charge. 3 minus. Much better. So phosphate is PO4 3 minus. We'll type that into the text box for those of you who want to review the notes later. Now we're going to use the crisscross method to get the right formula. So we're going to take the 2 from up here, stick it down there underneath PO4. We're going to take 3 from up there, stick it down underneath the Ca. So our formula is Ca3 and then PO4 with a 2 underneath it. And its name will be calcium phosphate. Okay, I don't know what that white box is. I don't want that. There we go. All right. Now, one more thing here. Some of you may have seen Roman numerals involved in the names. We only use Roman numerals for transition metals or very, very certain heavy metals. Also, let me warn you about this ahead of time because this is an edge case that may or may not come up during your exam. Zinc is always 2 plus and silver is always 1 plus. So neither of those need Roman numerals. Even though they are a transition, they are reliably the same state all the time. So if you see those don't need Roman numerals either. So some of you who've done some study on naming, maybe take a shot at this one. If you see diphosphorus pentaoxide, what do you think the formula would be for that? Diphosphorus pentaoxide. P2O5. That is the correct answer. So remember that di means 2, pent means 5. So you have 2 phosphorus and 5 oxygens, giving you P2O5. That's right. How about this? You want to take a shot at carbon tetrachloride? What do you think that one is? Carbon tetrachloride. Let's see, CCl4. That's right. So if you have no prefix, means you have 1 carbon and then 4 chlorine, or chloride, really. CCl4. So just to give those of you a list who are less familiar with this, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is nona, 10 is deca. I don't expect you'll have to go higher than 10. You will use this for non-metal compounds, stuff that's all non-metal. So that's different from what we did in the previous slide. Last slide, we had metals and non-metals. Here, you'll notice it's all non-metals. So use the prefix system if it's all non-metals, and then just name it normally if you have metals and non-metals involved. So what if they give you a Roman numeral? Okay. So if they give you the Roman numeral tells you the charge of that iron. And this is important. It doesn't tell you the charge of the oxygen. It just tells you the charge of the iron. Okay. So we're going to start off with iron 3 plus. Now let me ask the chat. Do you remember the charge of oxygen? Looks like you already got the answer. Yeah, you know where I'm headed with this, -2. You already knew this one, I think. Take the 3, stick it under the oxygen. Take the 2, stick it under the iron, and you get Fe2O3. Now for ammonium chloride, does anyone know what ammonium means? What's the symbol and what's the charge? NH4, positive, very good. You got it. So if we have ammonium chloride, we will have NH4 positive. And chloride, as we said before, was Cl negative. So you might notice that you've got a 1 plus and a 1 minus. And if you have 1 to 1, just put them together. So we have NH4 Cl. That is our answer for that. All right, let's see how many other naming questions I have here. Oh, yeah, what about acids? Haven't talked about acids yet. So here's how we deal with acids. So to write the name of an acid, you need some kind of polyatomic ion to go with it. Okay. And you need to pay extra special attention to the suffix on the acid. So if you see the suffix IC at the end of the acid, that means you're going to go to the polyatomic ion table and then look up something that ends in ATE, something associated with the acid in question. So if they give you bromic, you look for bromate. So who can tell me in the chat what the formula for bromate is? Yeah, this is one that doesn't come up as much. Bromate. BrO3, correct about that. What's the charge? BrO3 is the correct formula. Do you happen to remember how many negatives it carried with it? -1, very good. So we're going to say bromate is BrO3 -1. Get the eraser there. Make sure that comes out cleanly on the slide. BrO3 1 negative. Okay. And just to make sure that you know what to do with the others, if you see per, if you see per before the name, it means you are going to look for an ion that also starts with per. And if you see OUS at the end of the name, that's another one that could come up. Means you're going to look for an ion that ends with ite. And if you see hypo before the name, we're going to look for an ion that starts with hypo. Okay. And if you see hydro before the name, don't use a polyatomic ion. There are certain special cases where you would, but generally you won't. Okay. but look for something that ends in IDE. Expand this text box here. Now, well, I just want to make sure everyone had the guidelines for how to name those acids. So look for per, look for us, look for hypo, look for hydro. And of course, ic is the one that comes up the most. Now, once you've figured out what ion you're supposed to have, we need to add hydrogen plus to it and add 1 for however many negatives we have. So if you had -1, your correct formula would become HBrO3. All right, we'll do another example of that because I think that wasn't too easy. Let me get the slide ready. So for an additional example, we will find the formula for sulfurous acid. So, oh, let me spell it right. As we know, if it's wrong on YouTube, it's wrong forever. Let's fix that. There we go. So sulfurous acid, we know we're going to have sulfur in there. But the OUS means we have a polyatomic ion. Now let's have a look at our guidelines in. Our OUS guidelines, we're going to look for a polyatomic ion that ends in "ite." So we're going to be looking for sulfite. So check the chat here. See if make sure I didn't miss anything. I'll do a hydro example after this as well. Yes. But let's do sulfite first. What is the correct formula for sulfite? And what is the charge for sulfite? Does anyone know sulfite? Want to take a shot at it? SO3, that is the correct formula, and it is 2 negative. Very good. You got it. Sulfite is SO3 2 negative. And as we said, we also need 2 H pluses. So 2 H pluses with SO3 2 negative makes H2SO3. And that's the formula for sulfurous acid. So now hydro. Remember we said hydro was something of an edge case. So here's a hydro example. Get a new text box. So what is the formula for hydrofluoric acid? So your clue here is that hydro means it is probably not polyatomic. And it also tells you that whatever you're doing ends in IDE. I'll note that it's probably not polyatomic. There are a couple that are, but for this class, I don't think you'll see them. And then fluoric. What element would be denoted by fluoric? And what charge would it be? Again, don't check for polyatomic ions here. Fluoride, right? And as we know, fluoride is 1 minus. Now we know that, and I'll even write this as fluoride. And then all we got to do is just attach a hydrogen to it. So we're not using polyatomics here. We're just going to put a hydrogen on this guy. And so if you say HF, that is hydrofluoric acid. Let me just do a contrast here. If you did hydrosulfuric acid, you would not use SO3, you would use sulfide. And also, let me just draw a line here. Don't go to the polyatomic ion chart, you just go straight to the periodic table. So now, can anyone tell me what the charge of sulfide is on the periodic table? -2. Yep, that's right, you got it. It is -2. So you have S2 minus, and we're going to add hydrogen to that. So we'll have H2S, and that's hydrosulfuric acid. So do you see the difference? Sulfurous acid has H2SO3. Hydrosulfuric doesn't have any oxygen, just has S. And almost all of your hydro acids are going to look like that. All right, so we got the idea, I hope. Any other naming questions that you want to throw at me? Because I can make more up. If you want to do more transition metal stuff or polyatomic stuff, I can throw something together. Or any other questions about naming that you brought with you? And do another transition metal? Okay, we can do that. And we see more poly stuff. I can do that too. Okay, let's try it. So here, let's do some additional practice with another transition metal. So let me throw this one at you. Let's find the name of VCO3 2. All right, so first, vanadium, I will tell you, is a transition metal. This is an element I worked with back when dinosaurs ruled the earth 20 years ago. Back when I was in school, I did a number of experiments with vanadium, and all I managed to make was very expensive mush. Never did quite get what I was after with it because vanadium is stubborn that way. So we'll just say we have vanadium, and then we don't know what charge it is because it's transition. But CO3, what is that called? And what is its charge? CO3. Name and charge. What do you think? Carbonate is correct. And what was the charge? 2 negative. 2 negative is the right answer. So we'll say you have vanadium something carbonate. And for now, we're not sure what goes inside that parentheses, but we know something has to. So now to figure out what goes in the parentheses, we got to do algebra. Where V is unknown and CO3 is -2. So we set up an equation here. It says vanadium plus 2 pieces of CO3 together makes 0. So the total charge of the compound's got to be 0. 1 piece of vanadium, 2 pieces of carbonate. Now we know carbonate is -2, so we're going to plug in that -2 in this position. Set that equal to 0, and then 2 times -2 will give you -4. So that means vanadium is +4. And then we're just going to use a Roman numeral for, and that is IV in the parentheses. So your correct final name is vanadium 4 carbonate. All right. So hopefully this helps a little bit with transition metals. We can do one more example here. And let me clean this up. Put in another text box. So what if I ask you to find the formula for, let's see, manganese 4 dichromate. This one's hard mode. All right. But the good news is we have been told directly that we have manganese 4. So we'll write that first because we know what that is. How about dichromate? Does anyone remember that one? That one's rare. Some of you might remember it. CR204, you're close. You're right about the CR2. You may have made the mistake of confusing dichromate with regular chromate. Does anyone else want to take a shot at this one? CR207, that's the one. Yep, CR207, either you knew that one or you did some really fast Google foo. Does anyone remember the charge of CR207? -2, that's the right answer. All right, so now we can do the crisscross thinger. Take the 4 from up there, pop it under. Take the 2 from up there, pop it under. We'll have MN2 CR207 4. Now, let's see if the chat recognizes what's wrong with this picture. Because I got to do one more thing with this one. What do I do if I have a 2 here and a 4 here? What's my move? Simplify down, that's right. Divide both of them by 2, and my new formula is Mn CR207 2. All right. So now we've gone through quite a bit of naming. We've seen a lot of the major variations. Just remember that you don't have to use a Roman numeral every time just for transition metals. All right. So let me see what else people asked about. I want to make sure I cover what you requested. So we did some naming, do some reaction equations, oxidation states, and enthalpy. Okay. So before we move on, see any suggestions for memorizing polyatomic ions? Honestly, the best way to memorize polyatomic ions is to just do naming problems. Like staring at the chart and just reciting them to myself really didn't help me when I had to learn this back in high school. Like the idea, like the thing is like just like remember like repeating names to yourself and staring at them was really no help for me. So what I had to do was practice the problems and like practice how I would use them. And the more I practice them, the better I get at remembering them. But I would also say this. There are some of the polyatomic ions that are related. Like BrO4 negative is perbromate. BrO3 is bromate. BrO2 is bromite. And BrO negative is hypobromite. So if you can package them together like this and remember sets of them, that would be huge, I think. You can just see like all the difference between them is just how many oxygens. The base form of this would be bromate. And then adding an oxygen puts you at perbromate. And then taking away oxygens puts you at bromite and hypobromite. So if you can remember them sort of in sets that might be related to each other, that would help you a lot. Also, you may note that elements that are in the same group tend to make the same ions most of the time. So chlorate and iodate tend to look a lot like bromate just because they're all in group 7. So those are all things you want to keep in mind. All right, so let me see what was at the top of the chat here. Let's talk about. There are a lot of examples I've written where you'll need to write reaction equations. So let's definitely check that out. Oh, let's see, a lot of, there we go. So some of these get fairly involved here, but we can do some examples of like going from a word description over to an equation, and one where they start you off with reactants and they ask you to predict the products. So all of that's worth having a look at. So for example, if we were asked question A here, potassium chlorate decomposes into potassium chloride and diatomic oxygen gas. So we'd have to know how to translate those words into formulas, okay? Now, I will tell you potassium, let me just make a place for this. Potassium chlorate. Potassium is K1+. But what is the formula and the charge for chlorate? Does anyone remember that one? ClO3 and the charge? Negative. Very good. So together they make KClO3, and that is the first entry in our equation. And let me throw another question to the chat. If we have the word decomposes, do you remember what a decomposition reaction is and what it stands for?
breaks apart, right? So it's going to break into two things. And so if anyone learns from quizzes, I made one, went over it, and helped. That's an excellent idea. I'm gonna like that one too. That's solid. Yeah, absolutely do as much practice as you can. Like especially any practice that's not on WebAssign. Because WebAssign, I don't know if anyone's admitted this to you yet, but it's much harder to use than it has to be. Let's see, so we have KCl through LO3. Decomposes means it breaks into two things. Potassium chloride. That's K plus and Cl minus. So together makes KCl. And diatomic oxygen gas. So can anyone tell me what the word diatomic means? Diatomic. Two atoms, that's right. So if they ever say oxygen gas or diatomic oxygen gas, means two atoms of oxygen together. Sometimes they will just say oxygen gas and expect you to know what they mean. So if you see those two words next to each other, that denotes O2. Now, let's have a look at this equation I've written. Is this balanced, or do I need to make an adjustment? What do you think? You need to balance it, right? Because you might be able to tell the oxygen's out of balance. You got a 3 here and a 2 here. So 3-to-2 ratios come up a lot in chemistry. So mathematically speaking, if I have a 3-to-2 ratio, it's going to be hard to make those equal as it is. So those of you who've ever run into a 3-to-2 ratio when you're balancing, how have you resolved it? What number do we need to go for here? Because they can't be equal as is. 6, that's right. If you see a 3-to-2 ratio, you want to go for 6. So to make this 3 into a 6, we have to double it to make 6. So we put a 2 in front. Then for O2, we have a 2, so we need to triple that to make the 6. So we put a 3 in front of that. And that is how we write an equation based on a description and balance it. So we just have to get formulas for every set of words, write them down, and balance them. So now that we've done some practice with naming, you may be in better shape to do that. I am going to make a note here that oxygen gas always stands for O2. Well, oh, now that we've actually put a 2 in front of the KCl, that does mess up our KCl, doesn't it? You're right about that. So since you changed KCl, KClO3, you also have to change KCl. So you are right about that. 2 KClO3, 2 KCl, 3O2. All right, pretty good. All right, let's talk about complete ionic equations and net ionic equations. So let's start right there in part A. So we have two reactants, and the question asks us to predict the products. So when I do these, I want to start by breaking everything apart into ions. We can get a text box. For some reason, it's not letting me do the text box. 1 second. I think PowerPoint froze up for some reason. I hope I don't have to restart PowerPoint. Let me try Alt-tabbing. There we go. It just froze up for a second. Yeah, PowerPoint's kind of giving me sass right now. There we go. All right, so to start off, break everything into ions and write the charges. All right, clean this up. All right, so you have HBr. If you break that into ions, what ions should you get? And what charges would the ions be? So we need what are the pieces, what are the charges if you broke HBr? H plus and Br minus. Excellent. I'm going to write that down. All right. Now, what if I did the same thing to NaOH? What pieces would I get? Yeah, for NaOH. How would that break? I'm going to be careful with this one. Yep, you have OH minus. Good. And Na plus. Good. You got it. Write that down too. Okay, so we got 2 positive ions, 2 negative ions. So now, once we've done that, we are going to do this. We're going to put the first positive ion with the second negative ion. And then also put the first negative ion with the second positive ion. That's going to go something like this, where you're going to unite the H plus with the OH minus like that. And we're going to figure out what that makes. And we're going to also unite Na with Br, figure out what that makes. So if we take H plus, unite it with OH minus, we can see that's 1-to-1. We'll get HOH, which usually you write as H2O. And then we'll have Na positive and Br negative. Unite those together, and you'll have NaBr. So I'm going to make a note here in the text box. We are going to then, once you put the ions together, you can figure out what the product is. You can use the crisscross method, like we did before, if the charges are not equal. All right, so now we know our products are water and NaBr. So I'm just going to write this equation again. We'll rewrite the whole thing. We'll say HBr with NaOH yields water, NaBr. These were both aqueous, and then we haven't figured out what the states of water and NaBr are yet. So now we got to think about how to figure out those states. Either solid, liquid, gas, or aqueous. So let me first throw this to the chat. How about water? Do you figure that's solid, liquid, gas, or aqueous? Yeah, you're right. In most cases, water will be a liquid. Unless you're boiling it, then it's a gas. But in most of the time, it's going to be liquid. So water is almost always liquid. Unless you're running the reaction at 100 Celsius or higher. If you're running the reaction at 100 Celsius or higher, you're going to get a gas instead. In this case, we didn't give you a temperature, so you can assume liquid safely. So put a liquid there. Now, for NaBr, different story. Okay, for NaBr, we are going to have to run the solubility rules. Now, we hope you have them memorized by now, or at least mostly memorized. But if you don't, you can always look them up, at least until the exam starts. Once the exam starts, you have to remember them. So for NaBr, NaBr is either going to be solid or aqueous. If it is soluble, you'll say aqueous. If it's insoluble, you say solid. So I'm going to give you a chance to take a shot at this one. Think it over. See if you can remember those solubility rules. Do you figure that it's going to be solid or aqueous for NaBr? Okay, we have one person saying solid. You're not sure we can get the solubility rules. We have one person saying aqueous. We're tied. Sounds like most people aren't sure how to do this, so maybe I can give you a little more help here. Okay, let me just Google one up real quick. Actually, I don't like that table. Let's get another one. I don't think that's a good table at all, now that I look at it. I don't like that table either. Let's use this one. So it sounds like we're a little deadlocked on this one. So let me just give you this reference table. Let's clean that text box out of there. All right, so let's see what people have been saying while I've been doing that. So Br is soluble. And how do you know if it's solid or AQ? It's a group 1 metal ion, so it's soluble, I think. You are correct. I'm going to give you an emoji. You get the paperclip emoji because you're absolutely right. It's metal. So look down here at the last rule on this page. It says anything in, actually, I'm going to make a little note here. That's anything in group 1. Anything in group 1A. All those salts that involve group 1A are for sure soluble. It says several uncommon ones are not, you don't have to worry about that here. So for that reason, we are going to say it is soluble and aqueous. Okay, soluble always means aqueous, so we're just going to put a little AQ down there. All right. So again, if you don't know, look it up. Practice as much as you can. You can, if you can find a quiz online for it, that would be even better. Now, let's talk about how to do the complete ionic. For the complete ion, we break it all up. Except for solids and liquids. So HBr breaks into H plus and Br minus. NaOH breaks into Na plus and OH minus. H2O is a liquid, so you still write it as H2O liquid. And then NaBr is another AQ, so you break that up. Na plus and Br minus. And then for the net ionic, see if anyone in the chat knows this. What do I need to do to change a complete ionic to a net ionic? Cancel out. You're absolutely right. Remove the spectator. Also correct. So we're going to cross out the spectators. And the spectators are the ones that didn't do anything. So you might notice that Br negative is on the left, and the same thing is over here on the right, and it's not part of a new compound. So that Br and that Br, to get to the net ionic, we cross them out. Na is the same thing. That Na gets crossed out. That Na gets crossed out. So those are spectators also. We cross them out. And now we have H plus and OH minus remaining. Now, you still have H on the right side, but now it's part of a new compound. It was by itself. Now it's part of water, so that definitely did something. So your net ionic is H plus, OH negative, yields water, liquid. Also, one more thing here. If it's charged, for the purposes of your class, it is AQ. So the hydrogen will be AQ, the OH will be AQ because both of them have some kind of charge. Right. Yep, you guys got the idea about how to go from complete to net. All right. So let's check out, now that we've done some practice with that, let's try to do a little bit of acid-base stuff. So we'll get a little bit more practice in on this. So HCl with CaOH2. So first off, let's just try to do the same thing we did last time. Break this up into pieces. Let me get the text box and make a note of that.
insert text. Boom. So we're going to break this into pieces and get the charges of each piece. Okay. Then once we have all that together, we are going to reunite them. In a different order. Figure out what compound gets made. And then once we figured all that out, we're going to figure out if our products, oh yeah, we got to balance the reaction, of course. And then figure out if the products are solid or aqueous. All right, so let's start up there with HCl. If I break HCl up, what ions do I get? And what would the charges be? H plus Cl minus, very good. And now again for CaOH2. We have H plus, Cl minus. What about CaOH2 though? What's the charge for Ca? What's the charge for OH? Ca2 plus, OH minus, very good. And now we are going to unite H plus with the OH minus. As we saw before, this gives us water, and we know that's liquid. Okay, good. Everyone's got the charges down. Nice work. Now, what if we united Ca2 plus with Cl? Minus. Together, if I use the crisscross method, what should my formula become? Very good. You recognized it. CaCl2. So we would take the 2 from the Ca, put it under. We're going to take the 1 minus from there, put it under Ca, giving us CaCl2. Now, let's go ahead and check out if that is solid or aqueous. So this one's not easy to remember. But you might notice there is a rule for chlorine. It says all chlorides, bromides, and iodides are soluble. Except for silver, lead, mercury. Now we don't have silver or lead or mercury, so we're going to say this is soluble, and we'll say AQ after it. And the reason it's soluble is because of the chlorine rule. Right. A lot of you caught that too. So good work on that one. And it looks like someone's typing. I'll give you a second if you want to continue. Okay, well, don't worry about that later. So now our products are going to be HCl, AQ. Sorry, our reactants are going to be HCl, AQ, CaOH2, AQ, yields HOH or water, liquid, and CaCl2, AQ. Now, is this balanced? If it's not balanced, what do I need to change? Let's think about this. What do I have that's out of balance here?
Yep, the CLs are out of balance. Very good. You noticed it. So I have Cl2 on the right, but only 1 on the left, so I have to double this. Now you might notice that the H's are out of balance, so I also put a 2 here in front of water. Adding that extra H definitely threw us out of whack, but the extra 2 in front of the water fixes it. All right, pretty straight. All right, we have about 45 minutes left. I believe someone asked about oxidation states also, so we can do that too. So maybe let's talk about determining oxidation states. We did one of these earlier, but let's definitely run it again. So this first question asks us to find the oxidation state of sulfur in H2SO4. So we're going to say, and it also says using the usual rules for O and H. So you've got 2 H's, an S, and 4 oxygens. All together makes 0. All right, so what is the usual charge for H? What is the usual charge for O? I'll throw that to the chat. What do you folks think? The charge for H and the charge for O. +1 and -2. Very good. So in the H position, we say +1 plus S, and then 4 times -2 right here equals 0. If we do the math, we'll have 2 plus S, and then 4 times -2 makes -8. So for those of you algebra experts in the room, if I solve this equation for S, what answer would I get? +6. Very good. So you know more or less where we're headed here. The reason I ask this is because now we can start answering more complicated questions if we know how to calculate that. So for each equation, this question says to identify which atoms are being oxidized, which atoms are being reduced, as well as their starting state and ending state. Okay. So question A, we have CH4. Let's look at the left side first. We have CH4. Now, usually what we're going to do is we're going to assume, I'm going to get a text box here to write this down because that's important. We are going to assume that H is +1 and assume that oxygen is -2, except for in some specific cases. I haven't seen any of those come up in your class. I think they come in organic chemistry, but we'll deal with that when we get there. So, all right. If we assume H is +1 here, we'll have carbon plus 4 times +1 equals 0. If we solve that, what is the state of carbon? -4. Very good. And now if we go to the right side and we look at CO2, we have a carbon and 2 oxygens. As we said, oxygen was -2. Set that equal to 0. If we do the math there, What's my charge for carbon? +4, right. So do you see that from the left to the right, we have gone up in charge? And if you go up in charge, the word we use is oxidized. That's right. You knew that one. All right. So now get a clean copy of this. So that told us what happened to carbon. So we're saying carbon starts at -4, ends at +4. I'm going to make a copy of that reaction and move to the next page. Now, the reason why this might be confusing now is because now we got to look at oxygen. Now, on the left side, we had O2, the diatomic form. Here's an interesting trivia question. When oxygen's diatomic, do you know what the charge is supposed to be? Exactly right. It's standard state, so 0. And more importantly, it's standard state and it's by itself. It means it's 0. Now, if we go to the right side, oxygen is part of 2 compounds. But if it's not by itself, we can safely assume for the purposes of Chem 151 that it's -2. So if you go from 0 to -2, your state has gone down. And when your state goes down, you are reduced. And yes, that is the same for all diatomic elements. There are, I believe, 7 diatomic elements they ask you to know. All of the diatomic elements at standard state are automatic 0. So hydrogen, oxygen, chlorine, bromine, fluorine, iodine, all of those are automatic 0s if they're by themselves. And any element on its own at standard state is automatic 0 unless they give you a charge. Okay, so you got to be a little careful about that. So like if they say iron solid, that's a 0. But if they gave you iron 3 plus AQ, that's still an element by itself, but because of that AQ and the 3 plus, that tells you the charge is 3 plus. So any element by itself that doesn't have a charge written is 0. An element that does have a charge written, you use the charge they give you. All right. Is that a little bit better? All right. Now, here I've got some examples for oxidation and reduction half reactions. Oh, question in the chat. Why didn't we look at the H? I'll show you why we didn't look at the H. And I'll prove that we didn't have to. So again, we'll make a copy of this equation. So now, do you see how H is not by itself here? That means it's a +1. Again, except for a couple of edge cases, but again, not for this class. But do you see on the other side, it's still not by itself. And so it is still +1. So if you start at +1, but you stay at +1, you are not oxidized or reduced. All right. Do you understand why that is? Good. Now, if hydrogen is bonded to a 1A, 2A, or 3A metal, it can be -1, but that's rare. For your purposes, unless you're going on to organic chemistry a couple semesters from now, you can safely ignore that. Now, I want to ask you folks a question before we go on to enthalpy. Did any of you have to balance half reactions and add electrons and H plus and water to this sort of thing? I don't. I see. I wasn't. I saw it for Chem 152. I didn't know if you did. Okay, some of you did and some of you didn't. Yeah, sounds like maybe about 50, maybe about 50-50. See, this is where this is where like the teachers don't agree on whether to bring this in or not. So for those of you who did see this, I'm going to go ahead and do one. All right. So there are, I'm going to do part B here. Start with NO3 negative goes to NO2 negative. And I'm going to give you a checklist of things to check. Okay. So here's your balancing checklist. Number 1, you have to balance your metals if you have any. Then after you've taken care of the metals, you balance your non-metals other than oxygen and hydrogen. And once you've taken care of everything other than oxygen and hydrogen, you want to balance oxygen by adding water to whichever side has less. Then you're going to balance your hydrogen by adding H plus to whichever side has less. And then you balance your charge by adding electrons to whichever side is more positive. So 5 things to check in order to get your half reactions balanced. Like, got a question coming here? Any more time to type here? I'll let you keep typing. I'll keep an eye out for you. All right. So first off, we might notice that there are no metals at all. So we can skip the metal step. Step 2, balance nonmetals other than hydrogen or oxygen. So we look to our nitrogen. Just here. Okay, yeah, we can still do it for those of you who didn't see it. So let me ask the chat this to get started. Are my nitrogens in balance? Do I have the right number of them? Or do I need to make some changes to nitrogen? Yeah, so you're saying, yes, my nitrogens are in balance. Good. Now, next. So next I need to balance my oxygen. Which side has less oxygen, left or right? Which side has less? Correct. So we're going to come in, add water. Now that we've done that, move to step 4. Which side has less hydrogen? And how many less? Which side has less hydrogen? How many less hydrogen? Left, yep, left side needs 2, so we come in and add 2H plus onto the left. Now we check the charges. And you got to be careful with your math here. So on the left, if we have 2H plus and 1 negative, together, what would my total charge be? You're thinking 0? This is why we got to be careful about our math, because I think you're seeing the plus and you're seeing the minus, but you see there's 2 pluses. It's 2H plus 1. Very good. There you go. So our charge on the left is +1. Now on the right. Look on the right. What's my total charge on the right? -1. Good. So now, how far apart are they? What's the difference between +1 and -1? 2 charges. Very good. So let me draw a picture to go with that for those of you who are having trouble with the concept. I had to do this for my last student too. So on the number line, 0's here, -1's here, +1's here. So the distance between -1 and +1, you can see, is 2 marks. So we have a difference of 2 electrons. Yep, you see it. So now, since we have a difference of 2 electrons, we're going to add 2 electrons to the more positive side. So because our more positive side is the left, we're going to add 2 electrons onto that side. And so our final answer is this equation here. So for those of you who did balancing of half reactions, that's the order that you have to balance. Because if you do that out of order, you're going to run into trouble. For those of you who didn't see it, you might see it again if you take any more chemistry. All right. So let's go ahead and move on to enthalpy. So we're down to less than 30 minutes, so I may not be able to do all the enthalpy problems. So I've got a question on Hess's law, a question on heat transfer, heat of combustion, and then more heat of combustion.
So, did anyone have one of those three that they would rather start on? Do Hess's law, combustion, or heat transfer? Try Hess's law? I don't blame you. And heat transfer, okay. Okay. We'll do Hess's law first, and we'll see if we have time to do the other. All right, so Hess's law. I'm going to make this a little bigger so everyone can read it easier. All right, so we have a target equation. And that target equation is 2CO2 plus water yields C2H2 plus 5 halves O2. I'm going to copy that down here. All right, first thing we need to look for is make a pass through this equation and look for things that appear only once in the system below it, okay? So I'm going to refer to this set of equations as the system. I'm going to refer to the first equation they gave us as the target. And I'm going to refer to this as line 1, line 2, and line 3. And yes, the recording will be available on YouTube, and it will be available in the chat after we finish. I'll upload it to YouTube within the hour. All right. So, what we need to look for first is we're going to look for things. So first, look for things that appear in the target and only appear in the system once. Okay. So first, let's just look for CO2 in the system. What line is the CO2 on? And is it on the left or the right? Line 1, 2, or 3, left or right for the CO2? Line 3 on the right. Yep, let's make a note of that. We'll need that. Now, what about water? Where does water appear in the system? Be careful about this one. Yep, line 3 on the right, line 2 on the left. But more importantly, it appears on 2 lines. So we're going to say that we're going to write down that it's on line 2 and 3. And that means we're going to skip it for now. Let's go on to C2H2. What line is it located in? Left or right? Yep, line 1 on the left. Okay. And what about O2? You might notice that O2 will appear on multiple lines as well. That's also on line 2 and 3. So we're going to skip it for now. Okay. So now that we've done that, what we're going to do is target the ones that only appear once. And we're going to make some changes based on that. Okay. So what we're going to ask ourselves about the ones I boxed in. So let me just write down, we're going to box in the ones that only appear once. And then ask yourself 2 questions about it. Is it in the correct location with regards to left or right?
And also ask yourself, are there the correct number of them? All right. So let's look for CO2 in the system. Okay. We need 2 of them. Check the chat real fast. Okay, so you've noticed that the CO2 is not on the correct side in the system. So CO2 should be on the left. The fact that it's on the right in the system means it's on the wrong side. To fix that, we must reverse line 3. Now, how about C2H2? It's on the left in the system, but what should it be? Is it in the correct position, or do we need to change it? Notice that C2H2, in the target, it's on the right, but in the system, it's on the left. Change that too. Very good. So we must also reverse line 1. All right, so I'm going to make a copy of this. And now with that in mind, let's make those changes. Okay, so we've decided to reverse line 1 and line 3. So we rewrite them. We don't know what to do to line 2 yet, but we know we're reversing line 1, line 3. So line 1 is now C2H6 yields C2H2 plus 2H2. And the delta H is also going to reverse, and it is now positive 94.5. That's my new line 1. My new line 3 is going to be reversed as well. So that's going to be 2CO2 plus 3H2O yields C2H6 plus 7 halves O2. Make some more room here. The delta H for that is going to be 283 kilojoules. Now, we don't know what to do with line 2 yet. I'm going to make a little note of that. So we have 2 lines down, 1 to go. So we need to figure out if we need to change line 2. So we're going to now compare the system. We're going to compare the new system against the target. So I'll make a copy of the target again. This is when it gets a little bit tricky. I'll leave a space for line 2. And I'll write that's my target. We've taken care of CO2. We've taken care of C2H2. It's just that we're still a little in the dark about what to do with line 2. So here's what we need to look for. This is where it gets a little bit tricky. Copy this over. Make a new slide. And I'll copy over line 2 as well, because we need to know what to do with it. So there was my line 2. So now what we're going to do is look for things that have to cancel. And I'm going to try to think of a good way to say this to where it'll make sense. We're going to look for items in the system that don't appear in the target. See, because if they're in the system but not in the target, that means they must cancel. All right. So let's examine the system. And I want you to first have a look in line 1. Oh, is there a question down here? See, multiply by 5? Did you mean to say 0.5? That would make sense. Multiplying by 5 would be no help. But let me try to explain that to everybody else. So here's a question that I want to ask first. Look in line 1. Do you see something in line 1 that is not in the target? You're right about that, but you got that. Yeah, that's right. H2. Yeah, that's what I was going for. I think you see this. I think you're a little ahead of the rest of the group when you say that. H2 is not in the target. Okay. And there's 2 of them on the right. Okay. So H2 is not in the target, and there are 2 on the right. Therefore, we must change line 2 to place 2 H2 on the left instead. Okay, so now let's look at line 2. I'm going to now move this down. Moment. So let me just box that in. We have an H2. We need 2 on the left. Is the H2 in the correct position? Or do I need to switch this around? Should think about this. All right. I think someone's trying to type here. All right, I'll help you out with this one. We need to have we have H2 on the 2H2 on the right. We need to change this to put 2H2 on the left. So that means we are going to have to, number 1, reverse it, and also multiply by 2. See, it looks like someone said divide by 2 earlier. You actually want to multiply it by 2. Because if you make that change to it, if you reverse it, you'll have, like if we reverse it and multiply it by 2, we'll now have 2H2 plus 1O2 yields 4 water. Okay. Now, look here at the last line. Look here in the first line. You see the 2 H2s would cancel? Because one of them's on the left and one of them's on the right. That's good. We want the 2H2 to cancel. Okay. So we're going to now make a note of everything we did to the system. So again, I'm going to copy this down. And we're going to write down the decisions we made. So we said for line 1, we reversed it. For line 3, we reversed it. Oh. Clean this up. So line 1 was a reverse. Line 3 was a reverse. And then line 2 was a reverse n times 2. So my line 1 enthalpy is now positive 94.5. My line 2 enthalpy is now negative 71.2 times 2. That'll give me 142.4, and that's negative. And my line 3 was reversed as well, so that'll give me positive 283, and then you add that mess all together, and that'll give you your enthalpy. That's negative. Now, if you wanted to actually prove that the equation you got was the target, we can do that too. So now that we figured out what we're supposed to do here, copy all this, make a new slide. So now we'll talk about how to cancel this properly. First, I'm going to draw a mark between the left and the right so you can see where the left ends and the right starts. Right there. Okay, so the left will be on the left of the blue line. The right will be on the right of the blue line. You're going to check for anything that's identical on the left and the right. Get a text box here. So if you have this, we're going to check for anything that is exactly the same on the left and right. If so, you cancel it. And so the H2s that I've drawn the slash through fall into that category. They're exactly the same. There's 2 on the left, 2 on the right. Knock them both out. Also, we're going to check for anything, check for the same reactants with different numbers on the left and the right. So if you see those, you're going to subtract that amount from both sides. I should say subtract the lower amount from both sides. So I'm going to throw this question to the chat. Look on the left, look on the right. Do you see anything that has the same reagent but different numbers? Okay, we're seeing water and C2H6. Actually, C2H6, you might notice they're actually the same number because you have 1 on the left, 1 on the right. That can actually be canceled. So I'm glad someone caught that. Water is another one. We have 3 on the left, 4 on the right. And so we'll have 4 minus 3. And you see O2's on there as well. Exactly right. We'll have to do that too. So 4 minus 3 leaves 1 left. It will be on the right. And then we also see oxygen, O2. On the left, we have 1. On the right, we have 7 halves. So take 7 halves and subtract 1. What do we get? Yeah, thank you for coming. We're almost done here too, so we got like 7 minutes left. So 7 halves subtract 1 gives 5 halves. And which side will it appear on the left or the right? So basically what we're doing here, when we're looking at the O2, do you see how you have 1 on the left, 7 halves on the right? So what we're doing is taking the difference between them. Because essentially we're going to cancel 1 O2 on the left and cancel 1 O2 on the right. But you might notice that on the right, it's going to leave something behind. Because we can take 7 halves, subtract 1. So remember, we're only canceling the lower number. From the other side, we're saying, okay, if we canceled one of those oxygens, how many would we have left? And because it appears on the right side, we're going to say we're going to end up with 5 halves on the right. So this 7 halves changes to 5 halves. This 4H2O changes to 1H2O. And then the oxygen on the left cancels out. The water on the left cancels out. And now we don't really have that much left on here. Okay. Oh. Yeah, 5 halves on the right. Exactly. Good. All right. So let's look what we have left here. We've got, let's see, CO2. Oh, I might have written it backwards here. Make sure I didn't make a mistake at some point here. Oh, yeah, that was 2H2O, not 4H2O. So I actually wrote this down wrong. This should have been 2H2O. And so that typo might have messed a few things up here. So I'm going to say we have 2 water. Let's modify. So this was my mistake because I didn't write it down correctly. All right, so what we actually had here was 2 water on the right, 3 water on the left. This should have been 3 minus 2, leaving us 1 water on the left. So this becomes 1 water, and this water cancels out. And that was all because I wrote the wrong numbers down, which apparently I've been doing chemistry too long today and can't tell the difference between a 3 and a 2 anymore. That's the sort of mistake that you don't want to see recorded, but there it is anyway. All right. So all we have left on the left is 2 CO2, 1 water, yields C2H2, 5 halves O2. Yep,
It does. You just don't want to put it on YouTube, but I'm gonna have to anyway. I'll have to admit the fact that sometimes I hallucinate numbers. All right. But the important thing is we got the enthalpy. All you'd have to do is total up those enthalpies, and that would give you the final answer. All right. This was, to be honest with you, this was the killer problem in the set. What is my feedback to completing enthalpy? Let me think about that for a second. Actually, you know what? I think a lot of the when it comes to Hess's law, to be honest with you, like if I'm being 100% honest with you, on an exam for Hess's law, skip it and go on to the next question. Just because like it takes too long to do. Like, do the Hess's law question only if you have time. Get
I'm it sounds like a joke, but I'm dead serious. 100%. Like, go on to the next question if you can. Leave that for last just because there's so much proofreading and so much garbage going on with that question that your time is better spent elsewhere unless you're just way ahead of the game. Like the Hess's law question is what separates A+ students from A students. Unless you're that good at everything else in the course, it's not worth your time. I'd say get the stuff you can get, leave the Hess's law for last. Now, if you do have time, go ahead and take a shot at it. But look at all the stuff we had to do to make it work. We basically had, I think, like this first step where we figured out stuff that appears only once in the system, that's going to take care of most of your work. Because just by doing the first two operations, we locked down line 1 and line 3. It was line 2 that was the hard one, because we had to figure out how to manipulate it to get it to cancel properly. And yeah, I won't lie, it's that's definitely good. It was going to be a mess. There's no way for that to work out nicely, to be quite honest with you. So, yeah, if you're going to practice Hess's law, start on questions that are 2 lines rather than 3, because this was kind of a killer. All right, we are going to have to stop for today. We have another workshop tomorrow at the same time. I will hopefully see a number of you there. It's going to be on the same stuff. If you want to bring your own questions for the next one, you can. Anything so like tonight, mess around with WebAssign, with your any practice problems your instructor gave you. I am going to send you a copy of the slides that